Hi, my name is Saurabh Bagchi. I'm a faculty at Purdue University, and I'm telling you about a project that has started up on this topic of assured autonomy. And this is supported by the Army Research Lab. And this is a 5-year project that involves David, Mung, and Somali here at Purdue and Prateek at Princeton. So the main problem context for this is that in the Department of Defense, multi-domain operations are being stressed, and multi-domain operations will increasingly involve autonomous operations. These autonomous operations are going to involve different kinds of cyber elements, physical elements, and kinetic elements, and humans are going to be interacting with these different kinds of elements. So there are three unique differentiating characteristics of autonomous operations in this context. One is that we are not looking to secure just individual machine learning algorithms, but a pipeline of machine learning algorithms, which will work together to provide this autonomous operation. Then they have to execute in semi-real time, because humans have to react to the responses from these autonomous pipelines. And then they're not going to be executing on just one monolithic data center kind of an environment, but rather they're going to be executing on a heterogeneous mix of devices, from low-end sensor kinds of devices to tablet class of devices, edge computing devices, and even server class of devices when that kind of a network connectivity is available. And while the algorithms are executing in this autonomy pipeline, there are going to be various kinds of noises. These noises could be because of natural failures, the noise of being out in the field, as well as, importantly, adversarial attacks, both on the control plane and on the data plane. And these security guarantees, they need to be provided with latency guarantees. So it's because this is this requirement of semi-real-time operation, therefore the accuracy guarantees have to be provided together with the latency guarantees. And while there has been a tremendous amount of work on security and machine learning, the goal here is to, rather than look at individual attacks against individual algorithms and defenses for that, to try to come up with a design method through which you can argue that a certain class of algorithms against a certain class of attacks is just secure by design. Now, the autonomy is not a one-size-fits-all, but there are varying degrees of autonomy that come to play in here, from one where humans are in the loop, and therefore any software artifact must not overstretch the cognitive load of the human being. Some require humans on the loop, so they're not in the critical path for every operation, but they have the opportunity to introduce deviations from what the autonomous algorithm is forecasting or is suggesting. And then there are some which are going to be fully autonomous agents. So here are two sample pipelines, autonomous pipelines. One, in the first, you have a set of input streams coming in from radars and cameras and so on, which are then fused. Consider that these sensor streams will be at differing granularities, different fidelities, different characteristics like bandwidth, rate. Then an object detection is made based on the fused information stream. Then the object is recognized and is classified whether it's benign or malicious. And then after a threat assessment, then a kinetic engagement is initiated. The other kind is, again, you have different kinds of input streams, but now these input streams, some of these may be corrupted, and therefore the first stage of that pipeline is information filtering. And then information fusion happens. Then a situational awareness algorithm runs, which indicates which parts of the environment have been compromised, which parts of the computing and communication environment have been compromised, and therefore we should not trust them, versus which parts are still resilient and secure. And then based on this determination, the controller would decide to retask some of the compute capabilities, move it from this node to this node. retask the communication. So maybe we were originally relying on some ad hoc wireless mode of communication. Now we need to fall back into a longer latency but still available satellite mode of communication. And these multiple different ML algorithms in the pipeline will have different resource requirements, different input-output formats and characteristics, and they may be required to execute on vastly different platforms with different compute and communication capabilities. And it cannot be all enumerated a priori what kind of a platform each algorithm is going to run on. So it's important in the design phase to be able to create these designs and implementations which can flit between these different classes of execution platforms. So here's a high-level view. So when you talk about resilience, we think about resilience in two ways. There is the resilience by design, and then there is the resilience by reaction. In the resilience by design, you design and develop these autonomous systems from the ground up so that they are resilient to a large set of quantifiable perturbations. In the resilience by reaction, we acknowledge the fact that despite our best efforts, when deployed in the field, there are going to be certain kinds of attacks, perturbations that will arise, and the system will have to bounce back, react very quickly to these kinds of perturbations in the field. And a resilient autonomous system really needs to be built such that it has both of these characteristics. So there is the close interaction during the design and execution of the two aspects. And importantly, there is a learning capability in these systems whereby something which was resilience by reaction now gets learned and fed back into the design process. So now the boundary of the kinds of attacks, perturbations that the system is resilient against by design increases. So it's a learning process in this. And this vision paper written by about 15 of us lays out our vision for resilient autonomous systems. So what we have here at Purdue is a testbed for evaluation of assured autonomous protocols, starting from low-end embedded devices like system on chip with ARM class of devices as well as low-end GPUs, to slightly higher-end sensor actuator devices, to wearables. Then we have a sensor edge cloud platform where we have a set of edge devices which are connected to the cloud. And then these devices are actually installed and deployed all over Purdue campus. And this provides us with a fantastic testbed with realistic environmental constraints and conditions and requirements to experiment with our protocols and algorithms. And this network integrated testbed is network accessible and programmable with the right kinds of security guarantees, security firewalling, so that we can have controlled experimentation of assured autonomous algorithms. So now let us quickly take a look at the requirements for assured autonomy that we've set for ourselves in discussion with our Army Research Lab colleagues. So these ML algorithms must be capable of executing on a distributed set of execution platforms. As I mentioned, these could be either ground-based or aerial and with varying capabilities. And these algorithms must be trained offline, of course, the regular batch mode of training, but you should be able to incrementally train them in the field as well. And while you are training, you have to be cognizant of the fact that there is going to be varying amounts of noise, which is either artificially injected because of malicious purposes or just natural noise, which will be there in the data on which these algorithms are being trained. The autonomous algorithms will be interfacing with humans, and therefore they have to be built in such a way that they can interact with humans at two different levels. There is the tactical level of interactions, whereby the human would need to respond in semi-real time to the outputs of the autonomous algorithms. And then there is the strategic level of interaction, whereby the algorithms outputs, the assured autonomous pipelines outputs, will be used to make changes for future missions. The third one is we need to be able to reason about and provide probabilistic guarantees on both the accuracy of the algorithms and the latency. And these guarantees must hold, of course, under benign conditions, but they must hold under adversarial conditions when there is active attack going on in the system. And these guarantees must hold for both batch mode and incremental mode of training. The sensor streams that are being fed into these algorithms are quite diverse, and they would vary in different dimensions like fidelity, rate, characteristics. And these data sources would be intermixed, coming from white, blue, or red networks. And as part of the inferencing on it, our target is to be able to discriminate which is what kind of a data source, and therefore to be able to eliminate the impact of red data sources, the compromised data sources, for future inferencing actions. So one sample result that we have in this space is anomaly detection, which has been rephrased by us as distribution shift detection and localization. So the details are available in our NeurIPS paper, which appeared in November of 2020. And here the problem context is we have a set of sensors which are deployed over a large geographical region, and in an environment where some of these sensors may be compromised. So we want to identify that, yes, certain sensors have been compromised, and then we want to localize which of these sensors have been compromised. So our solution approach takes this 5-step process. First of all, we look to see if there is a distribution shift that has occurred. And this is a time series of sensor values. If the distribution shift that has occurred, this is detected by looking at a conditional distribution change in some of these sensors. The key idea is that even if some of the sensors have been compromised, the conditional distribution of some of the legitimate, uncompromised sensors would vary from the benign case to the malicious case. And the key technical contribution is we performed this using a test statistic-based method based on the density model score function, the Fisher's test statistic. And this is very efficiently computable and in a one shot for all the dimensions of the data. And then once we've identified that some of the conditional distributions have gone awry, then we identify which are the nodes which are probabilistically most likely to have caused this conditional distribution to have gone awry. So looking forward now, the 5-year project with the Army Research Lab collaborators is going to have 3 thrusts of inquiry. The first thrust is, how do you design these autonomous algorithms to be robust against a bounded set of adversarial actions, but you can reason about the robustness. The second one is, how can you have interpretable outputs from these algorithms? Therefore, the trust of the user on the results of these autonomous algorithms is going to be heightened. And then how do you enable these autonomous algorithms to flexibly execute on a diverse, heterogeneous set of computational platforms, and based on dynamic conditions to be able to flit back and forth between these different kinds of devices. So this is an ambitious and hugely promising direction of work, we believe, and we have a great team in place, and we are really looking forward to working with our team and the ARL colleagues to solve these really challenging but hugely potentially impactful problems.